So in this video, we're going to look at three-dimensional vectors, and we're going to compare them to our two-dimensional vectors and learn how to graph them, and then we are going to calculate the magnitude of three-dimensional vectors. So the first thing we're going to do is look at a three-dimensional coordinate plane. And so what we're going to do is we're going to have our two-dimensional right here, and then what we're going to do is extend a third dimension out. So if you look at this, there's kind of a flat back behind us, and then there's a axis. That dotted axis is coming right out of the page into our faces. And the convention for labeling these axes is actually a little different than we may expect, but it's nothing too crazy. So what we do is we have our x and our y, just like in two-dimensional where we had the x and y axis. But now what we've done is we've added the z. So if we were to think about this now with our letters, if you were looking down on a table, let's say, you'd have your x and y plane, and then z would be coming up out at you. Or back to our page analogy, the zy plane is in the plane of the page, and then the x axis is coming right out at us. So one thing I want to do is let's just take a look. What if we were looking down? If we're up here, and I'll try and draw an eye, and looking down on the table, what we'd see is this. And this should look familiar, although it might look a tiny, tiny bit different, but what's that? If we're looking down, right, looking down, what do we see? We see the xy plane. We've seen that before, so it's just a two-dimensional plane. All we're doing is adding that third dimension, so we're going to pop out of the page. So that's a good exercise sometimes to make these three-dimensional situations feel a little simpler, as we can turn them into a two-dimensional with just a little extra piece that we can think about. So when we talk about vectors, our 2D vector looked something like this. It would be some x component and some y component. Well, now for 3 dimensions, it'll look very similar, but we're just going to add a little piece, right? So we've got our x component, our y component, and our z component. So in the case that I've drawn here with this axis, the x is going to be coming out at us, the y is going to be moving to the right or left, and the z is going to be going up or down. So that z part is our up or down, all right? So that's how we're going to think about these vectors in three-dimensional space. So now what I'm going to do is we're going to move down a little. If I can move this, there we go. We're going to move down, and let's look at right there. So we've got our three-dimensional vector, and let's look at an example. So we're going to look at this vector. We're going to draw the vector. Let's just draw 1, 2, 0 first. So this is saying I've got my three-dimensional plane, right? As soon as we see 3 components in a vector, we know we've got 3 dimensions. So this will be my x, this will be my y, and this will be my z. So this one should look kind of similar to something we've seen before. We've got an x component of 1. So since this is the positive x-axis coming out at us, there's actually a negative x-axis as well. It's going back in through the page, away from us. And the same thing, the negative y we could draw going over this way. So this could be my minus y, and my minus z could be down. All right, so there's still negative components, just the diagram gets a little confusing if we add all those in. So I've just done the positive axes, and we'll just do examples with positive numbers for now. So what I need to do is the same thing we did in the past with 2 dimensions. So it's 1, 2, 0. So my x I know is going to be 1, so I'm going to come 1 on this axis. And then, so I know I'm along there somewhere, and I'm going to come 2 on the y. So 1, 2 on the y. So that point is going to be right there, and my vector is going to look like this. Notice, I don't have a z component in this one, so I'm not going to go up at all. Remember, the z is the up or down component, so this should just look like a normal vector that we've seen before. And if, again, let's do the exercise where we look down. If I look down, what I'm going to see is, well, I hope it looks almost exactly the same as what we've seen before. We're going to come over 2, 1, 2, and down 1. There's my point. There's that. Now, I understand if the positive x and y is throwing you for a loop. I know it's different, but remember, it's just has to do with convention. So in the normal xy plane, just by convention, we call the positive x right and the negative x left and the positive y up and the negative y down. It's kind of a different convention with 3 dimensions, all right? So just remember that the positive x-axis typically is coming out of the page into your face, the positive y is going right, and the positive z is going up, and that should keep you out of trouble. It's all about the way we decide to name things. So again, you could call them really whatever you want. We're just going by mathematical conventions so that other mathematicians can understand what we're saying. So there's that vector. Notice there was no z component, so all we did was worry about a vector in xy. So now let's look at one that actually has some kind of component for z. So let's look at, get those out of the way. Let's look at, oops, get rid of that. Let's look at another example. So here we have 1, 2, 3. Okay, so now we're going to go through the same steps. Here's my y, here's my z. We get a nice little x coming out of the page at us. And I'm going to go 1 in the x, 1, 2 in the y, and how many in the z? 3. 1, 2, 3. So the easiest way to do this is to do your x and y first. So 1 and 2 are going to meet right here. And then I need to go up to 3. Now this, I'm going to do my best job to draw it, but basically you're going to do a straight line up. And since this is out of the page a little, it's going to look like it's slightly below 3, but that's just my best 3D representation of that. So the actual vector is going to be that line. Let me do that over in red. So it's going to be, that's my vector. And we could come up with, this is the xy vector right there. And there's our 3-dimensional vector. I apologize if it doesn't look perfect, but basically it's going to come 1 out of the screen towards us, going to go 2 to the right, and then 3 units up. So there's a 3-dimensional vector. It's actually popping out of the page a little bit at us. So now what I want to do is talk about how to find the magnitude of these vectors. So let's shrink that and move it over here. And then let's talk about magnitude. Magnitude. So let's remember that for a 2D, the magnitude was just, let's say we had a vector, let's just call it a comma b. The magnitude would be the square root of a squared plus b squared. And remember that essentially came from Pythagorean theorem, where we could make a right triangle with that vector and find its hypotenuse, which was the magnitude. Well, in 3 dimensions, things are going to be a little different. In 3 dimensions, what we're going to have to do is consider that last part. So what I'm going to do is let's go back and look at this. Zoom right in there. There's our 1, 2, 3 vector. And what we want to do is we need to figure out the magnitude of that thing. Well, we can't just find the magnitude in 2 dimensions, or at least that won't be sufficient. But what we can do is let's find another right triangle. So what I've done, what we did before is we drew, I'll put a little arrow, that vector, right? That was the vector in the xy plane, all right? And then from that point, all we did, since we know the z value is 3, is we just went straight up 3. So since the z plane is perpendicular to that xy plane. I know that's a little tricky to think about, but think about the xy plane as your desk, and it's flat on the desk, and then the z would just be going straight up from the desk. So the z plane is perpendicular from that xy plane. So then if we have a vector in the xy plane, and then we look at how it changes up into the z plane, there's our right angle right there. Those 2 vectors are perpendicular to each other. And furthermore, I think we can find the magnitude of those and then make a new Pythagorean theorem problem. So what we're going to do is we're going to draw our new right triangle firstly. So I'm going to take this right triangle over here and let's redraw it. So in 2 dimensions. So there's our right angle. Now this bottom part is going to be from the xy plane. So that's going to have a magnitude of, well, we should probably find that. We can find that in 2 dimensions. So the magnitude of that vector is going to be, well, The x value is 1, so 1 squared, and the y value is 2, so 2 squared. So that's going to be root 5. So this is a root 5 right here. And that height, we said, is just simply the z component, so that's just going to be a 3. And here, I'll do a big capital M. That's the magnitude of our three-dimensional vector. We've turned it into a two-dimensional problem, which is nice. It makes it easier for us. So that magnitude, we can just use Pythagorean theorem. So let's do root 5 squared plus 3 squared is going to be big M squared. So it looks like we get 5 plus 9 is big M squared. So M is root 14. And there's the magnitude of our three-dimensional vector. So now what I'm going to do, let me shrink this back up. We'll put it over here. So now what I want to do is we want to derive, see how we have this nice formula for the two-dimensional vector? I want to come up with a nice formula for the three-dimensional vector as well. So let's take, an easy way to come up with a formula is to just take a generic vector. So let's take the vector ABC. Let's use ABC as our vector. So here we go, A, B, C. What we need to do is try and figure out how to find the magnitude of that vector. Well, let's follow the same steps we did in that previous example. What we're going to do, let me draw my best axes again. That wasn't very good. And there's my x, and there's my y, and there's my z. So I don't know exactly what the values of A, B, C are, but let's just say A is over here, and B is over here, and C is up here. So what did we do last time? And I'll use blue here. So first we had to find where A and B are on the xy plane. And then we had to go straight up from that to find our C. So we've got this, remember we made a right triangle there, and then I'll do red to show the actual the vector that we want is right there. So there's our three-dimensional vector. Now let's go through the steps we did before. So we need to find first the magnitude in that xy plane. So I'll call it little m. That's going to be, we did that before, the square root of a squared plus b squared, right? Then what we had to do is take that, and remember we can redraw our triangle, and let's just pretend that blue and red triangle just got smushed onto one page. So we've got our z component is going to be that side, and then this bottom side is that square root a squared plus b squared. And we're looking for, let's call it big M. We're looking for big M. So I think we're ready to just do Pythag again. So, oh, this is not B. I apologize. This is how far we go up, which is C. That looks better. So this right here is our C height. Okay, good. Now we're on track. So if I wanted to find that, let's just set up Pythagorean theorem. So let's do the square root of a squared plus b squared. Let's not do equals. Plus, and we have to square that, right? That all squared plus c squared equals big M squared. Well, something neat happens over here. So that whole thing is square rooted, and we're going to square it. So that gets rid of that square root, which is nice. And then plus c squared is m squared. So check it out. Big M is just the square root of a squared plus b squared plus c squared. And then let's compare that. We'll circle it. Compare that formula with our two-dimensional formula. Does it make sense? I think so. For the two-dimensional formula, all we did was take the squares of individual components and add them together and take the square root. And for 3 dimensions, we're going to do the exact same thing. So hopefully that's a little intuitive. Going through the diagrams hopefully helps as well. But now you can draw a 3-dimensional vector and you can find its magnitude.